So I think we can, after this session with the industry, we can move to the next speaker. So our next speaker is Professor Josefine Proll, who I see already on the screen. So Josefine is a lecturer here at the University of Eindhoven, but also she is working at IPP Max Planck Institute in Germany. So Josefine, thank you for being here with us, and please, the floor is yours.
All right. Yeah, thank you so much, Dario, for the introduction, and thank you, Dario and Mira, for inviting me to give this talk. Yeah, fair warning, I'm a bit under the weather, so I hope, you'll forgive me if there's a few bits in the talk which are, in case something goes wrong, just as a warning. All right, let me share my slides with you. And where is my Zoom now? Sorry. It's been so long, like the pandemic is too long ago, clearly. All right. Oh God. Now I'm kind of.
Yes.
Yeah, okay. It's a bit somewhere else. Anyway, you'll watch the slides and not my face anyway, right? So it's okay. Cool. All right. So I've been invited to give a talk, generally, really. And I was feeling like I want to give an introduction to stellarators. I'm not sure what everyone's background here is, right? So like whether you'll be like, oh, I'm so bored. I've heard about stellarators in forever and I know everything. Then this talk might not be for you. But I heard this talk is also for people who might be considering getting into fusion, and you guys are the ones I want to catch. But also, of course, all the tokamak people who are considering to change to the good side. This is your invitation to do so. So first of all, and I'm really hoping this works because Mentimeter is always please go to menti.com, like use the QR code and, give me some keywords that you know about stellarators. Can anyone give me like feedback of whether this is working or not? Hello? Okay. You know nothing about stellarators? That's amazing. Okay, cool. That's good to know. Star, yes, love it. Stable. Excellent answer. Star maker, very good, very good. No current, hard to build. Yes. Ooh, yes. Steady state, so important. Confinement through coils, yes. What else we have? Complex coils, so true. Helias, very clever, very advanced there as well. Best option, oh, I love you. Whoever said that. Elegant plasma handling, so true, so true. So much knowledge there already. Okay. Okay. Oh God, I can't follow anymore. Better than the tokamak. I hope there's no tokamak people here, but yes. Losing the symmetry. Yes and no. We'll come to that in a second. ITG turbulence. Yes, as well. But then tokamaks have those too. So Venetian 7X. Yes, beautiful. Also so true. So true. Twisted coils. Neoclassical transport. Yes. Oh God. So true as well. Cool shape. The dark side. No. We're the bright side. Like think of Star Wars. We're like clearly the good side here. Elegant plasma handling. We've had that. Oh my God, MHD islands. Yes, that too. Yes, difficult to build is like a recurring theme. I would say we stop this here. Thank you all so much for your responses. PPPL. Oh yeah, very good. And I would say we continue from here. I hope I'll address quite a few of these points. I see there is a lot of knowledge there already. Yeah, let's continue with the talk. And yes. So in general, what is a stellarator? So a stellarator is, first of all, let me switch on my laser pointer, is a plasma device, a toroidal magnetic confinement device, where the magnetic fields are, where the magnetic field forms nested closed flux surfaces, right, like in a tokamak. And the magnetic field is primarily generated by coils external to the plasma, so we don't need a plasma current. There's several questions why one would want to build one. First of all is to generate electricity, and it has, as we've already seen in kind of the big word cloud per Mentimeter, inherently steady state operation because of the no plasma current required. This also means there is a low vulnerability towards disruptions and low recirculating power required. So this all kind of aids to help in terms of safety, which really makes it a really great reactor candidate. But then of course there's also the other side, right? Like, of course, we want to make fusion kind of to, you know, solve the world energy problem. But on the other hand, one can also perform really amazing plasma basic research. For example, one can investigate single species plasmas or pair plasmas, so positron electron plasmas, which is also very, very cool. Just very briefly, why do we even need magnetic confinement? So as I hope most of you know, in fusion, we kind of need incredibly hot temperatures, high temperatures to achieve the fusion of the deuterium and the tritium. The temperatures are so high that we don't have material that could withstand the these high temperatures. So we use magnetic fields to confine our hot plasma. We can do this because the particles follow the magnetic field lines. So if we have no magnetic field, the electrons and ions would just shoot through our vessel. And here we have indicated the vessel with this cylindrical shape. But if we introduce a magnetic field, both the electrons and ions are bound to the magnetic field lines on spiraling orbits. The electrons have a much smaller orbit than the ions, and this is still, like, you know, not quite fitting. So there's a factor of 40 between these two. And I'm seeing you're writing something in the chat. Okay, never mind. So yeah, I'll not check the chat for now, right? So in case you want to communicate with me, shout, please.
Yeah, I mean, the people are still asking questions from the previous panel, but I will let you know if there is a question.
No, okay, very good, very good. Okay, cool. All right, so with a magnetic field, we can prevent the particles from touching the wall. This is due to the Lorentz force, but kind of seeing the response, I'll skip this bit ahead a bit. Now the main idea is, of course, well, how do we create like a magnetic field? You build really big Helmholtz coils, really, which create this beautiful straight magnetic field. But then you have the issue that the particles are still hitting the end points, right? And you could have magnetic bottles here, for example. So like make your magnetic field much, much stronger, but you'd always have particles escaping. So people came up with this idea of just taking the cylinder and bending it around. So it's a quasi-endless configuration, but particles are lost due to drift motions. So you can already see here that the magnetic field coils are much closer to each other here on the inside than they are on the outside. So immediately you just see by looking at this picture that the magnetic field strength will be much higher here than it will be out here on the outside. And these differences in magnetic field strength come with drifts. So the particles will kind of slowly drift out of the plasma here. And this is, of course, something we don't want. One explanation for like where this drift comes from, or like how this really kind of occurs, is that because of this gradient, the positrons are moved upwards and the electrons are moved downwards, and together with the background, so like this kind of creates an electric field, and together with the background magnetic field, this creates a so-called E cross B drift. And this E cross B drift is in the same direction for electrons and ions, which is particularly horrible, because this means that both electrons and ions will drift out of the plasma as a whole, basically, and then you lose the particles, you lose confinement. One way to overcome this is to create a twisted magnetic fields. And it's like, you know, as fusion scientists, we always kind of try to come up with ways to, you know, make this as an image. And one image would be if you have like one of these old-fashioned spoons for honey. If you kind of just take it, then the honey drips down. But if you twist it, then the honey will stay on the little spoon. And in a similar way, you can imagine that these particles, imagine like they're following one of these field lines, and imagine they'd be dangerously close to drifting outside here, but then the magnetic field line moves the particle back to the inside where they're back in safety. And then if they then drift radially outwards, they're actually drifting into the plasma. So if we have a twisted magnetic field, then we're basically safe. So if we then investigate our magnetic field of a stellarator, kind of in more mathematical terms, we can split our magnetic field into two components, and they basically just have to do with the direction of the magnetic field, basically which coordinates we choose. And these very typical tokamaks coordinates come actually from tokamaks more, so they're slightly less applicable to stellarators, but still sometimes used. One is the toroidal magnetic field, so that's really the field that's only in the direction around the axis. And then we have the poloidal magnetic field, that's the one in the short direction around the axis. And the ratio between the two tells us is the so-called rotational transform. So basically the amount of twist, or in tokamak speak, the safety factor. Now there's two basic ways to create a twisted magnetic field, the tokamak and the stellarator. But both of them need to somehow create this twist, right? And just as a reminder, that the twist, this rotational transform, is the number of poloidal turns you make while you make one toroidal turn. So you kind of go around, you follow a field line, and you count how many poloidal twists do you make while making one toroidal twist. And we have here examples. So here we have one example where we're going around the torus once, and we've done exactly one poloidal turn. I'm so sorry. Still tired. And there the rotational transform is 1. Here in this case, which is ever so slightly more chaotic, we have a rotational transform of 3.5. So we kind of twist slightly more than, like, we twist 1.5 times basically while going around toroidally once. Now, how do we do this? How do we create a rotational transform? And there's, in general, 3 different ways to do it. On the one hand, we could have a current, and this is basically like a fairly famous finding. So on the one hand, we could have a current, and I'm sorry for this very bad picture quality. I didn't see this before, but having a current inside, this is how a tokamak creates a rotational transform. If you have a current, and you see this ever so slightly here with these red arrows, this is supposed to be the current, where the current creates, you can have a right-hand rule, current in the thumb direction, and then the magnetic field in the direction of the fingers of your right hand. So this would be then what you don't see here. There's like blue arrows that are kind of pointing in the toroidal direction. And then together with the toroidal field, which is here in green, you get the twisted field in yellow. So this is how tokamak does it. Has some issues. We're not getting into that too much. Another option would be you take an ellipse, for example, as your cross-section of your plasma, right? So like in the tokamak case, this cross-section is often like a circle, and then it just kind of goes around like without any rotation, or it's a bit of a D shape, right? In stellarators, sometimes we use ellipses, and then if you then rotate this ellipse, then this gives you a rotational transform. This is, for example, done in the Large Helical Device, in the big stellarator Helitron in Japan, that's still currently operational. And here we have a visualization of how that's done. Another option is to twist the magnetic axis, and the most famous example of that is actually the very first stellarator that was invented by Lyman Spitzer, the figure 8 stellarator. And here the idea is that if you kind of, think of a tire, like from your bike, and think of it as like very, very flexible, and you would kind of twist it around, then this is exactly what you would get. And then this arrow here is kind of basically the direction in which your magnetic field would be pointing then. So this is also how you get rotational transform. Now, How did stellarators come about? Well, there is rumors, right? It's always really hard to say like when something was invented. But with stellarators, people are fairly certain that it was Lyman Spitzer was really bored on the very slow ski lifts in Aspen, Colorado. He had lots of time to think. Must have been really cold as well. And then he came up with this idea that you could have really good confinement by making this figure 8 stellarator here, basically without the need for a current. So in the end, stellarators are similarly old as tokamaks. And then they were introduced to the world in 1958, basically when certain documents related to Project Matterhorn were declassified. There were quite a few stellarator experiments, especially in Princeton. So Princeton was really the front runner for like quite a while, really as part of Project Matterhorn. So like we had this figure 8 stellarator here, then they made the so-called racetrack stellarator, the Princeton Model C, which is a bit simpler. And then some more shapes, so like another figure 8 stellarator, another figure C stellarator, or like another racetrack stellarator. And this was all quite fine, and there was like a lot of enthusiasm. Then the Germans started getting into it, so they kind of copied this first simple design of the racetrack stellarator, but then they soon kind of continued with more advanced scenarios like Wendelstein 7AS, starting with the twisty coils, but that was significantly later already. And then since 2015, we have Wendelstein 7X, the most advanced stellarator in the world at the moment, with very twisty coils and even more twisted fields than Wendelstein 7AS. And just as an anecdote, the name Wendelstein is, of course, sounding very German, but it's also a mountain in southern Germany. I think it was kind of chosen as, like to kind of mirror the name of Project Matterhorn, even though that was like a bomb project. So I'm not sure it was like the wisest choice. But then I wasn't there for that. Also, it means twisty mountain, which I think is kind of cute, or twisty stone, which I think is very appropriate for stellarators, which looking at this you couldn't quite tell, but so there is really various ways how we can create stellarators with different coils. So you can get very creative, right? Because you can also kind of, you can have the current, I mean, like, let's ignore the current, but because you have different ways to create the rotational transform by like either twisting your axis or by rotating your cross section. So here what we have is we're twisting the axis, as you can see here. So the purple thing, so this is the TJ2 stellarator in CMAT Madrid. The purple thing here is the plasma, and you can immediately see, right, like the magnetic axis kind of twists through it. So there's clearly a twisted axis going on. It also seems like the cross section is rotated. So that's also both of them. And here they have like a wild combination of different coils. So they have like very simple coils, which are kind of stacked in different heights. And then they also have very close to the plasma some additional coils that go all the way through the plasma. But like really most coils are circular and planar in this case. Then we can have purely helical coils, as it's done in the large helical device that we've already seen before. This is the idea where we're rotating the ellipse, right, around our surface. You can't quite see it. Well, I mean, I guess you can. So these are actually two coils that are kind of intertwined. And in the case of LHD, the currents run in both in the same direction, but you can also sometimes have them in opposite directions, depending on what you want with your magnetic field. Then you can, as I said, you can get really creative. This is the CNT, the Columbia non-neutral torus, which is probably the simplest stellarator ever built. It consists of 4 circular planar coils. So you have like these 2 big ones, and then you have 2 interlinked ones and tilted. And then the plasma kind of wraps around those. You can immediately see that this is like engineering-wise probably a nightmare, but it does create a very elegant plasma in a very elegant way. Then you can get also more engineering-y by creating so-called modular coils. So modular coils are, you abandon this idea of beautiful, simple, straight coils, and you go for kind of twisted coils that are much more able to generate a magnetic field as you design it. And we're coming to the whole optimization idea later on. So HSX is the helically symmetric experiment in Madison, Wisconsin, this way around. Here we have this combination. So you see the copper colored coils here, which are the twisted coils. And then in addition, they have straight coils to kind of help, or planar coils to help in experimental flexibility and to help with the main field. And here in Venetian 7X, a similar approach. Here we have, again, twisted so-called modular field coils. So like here, the red coils, and then on top, separate planar field coils for the experimental flexibility. Here in Venetian 7X, the difference is that all these coils are superconducting to allow for particularly long operation, which is really something that tokamaks really can't do. So this was very important for stellarators to show that, okay, we've gotten rid of the current. Now let's demonstrate that we can actually run this machine for a really long time. And you can't achieve this with copper coils. Even more creative ways to do this. We can also use permanent magnets. So here we see the Muse stellarator, which is actually operational in Princeton Plasma Physics Laboratory since I think half a year now or something. And it's this really unique combination. So we still have like very simple coils here kind of shown in gray. And then in addition, they have like a surface in which they insert little super simple strong magnets, so like the ones you could kind of buy to kind of, you know, like not quite for your fridge. They're like a bit too strong for your fridge, but like, you know, like you can kind of buy the little squared kind of magnets, and they just kind of put them into like a 3D printed surface and then create a really nice magnetic field. It's really quite amazing. Yeah, I mean, with all these cool advancements, you might ask like, but like why aren't stellarators, you know, why isn't either a stellarator? And trust me, I've asked myself that too. Well, there was a reason, because actually fairly early on, in the 60s, the Russians built a tokamak which had such good confinement, reached electron temperatures up to 1 keV, and these were values that no stellarator device until then had even come close to. So clearly they were doing something way better, like fundamentally different and fundamentally better than stellarators. This has to do with quite some maths. And I hope I won't lose you here, but like I'm a theoretical physicist, so I have to show a bit of this. I hope you forgive me. If you write down the single particle Lagrangian, so like the Lagrangian of a single particle that's moving in the magnetic field of any fusion device, it'll have, like in general, like this very simple form, right? And then you can write down the Euler Lagrange equations, you know, and we don't need to know much about the, like exactly how the Lagrangian looks, except for that we can say something about the angular momentum, right? Which is really like the momentum in this direction, which of course is related to the derivative of the Lagrangian with respect to the toroidal coordinate phi. If somehow the Lagrangian doesn't depend on phi, which is the case in toroidal symmetry, right? Like if there's full toroidal symmetry, nothing in our Lagrangian could ever depend on the toroidal coordinate, right? Like if there's symmetry, nothing depends on phi, then this here becomes 0. Then this means P of phi, like the derivative of P of phi, is also 0. This means that this is a constant, which means if the toroidal momentum is a constant, this means that particles don't drift radially outwards, right? Like if think of, you know, like wherever you've had to do with like angular momentum, this always kind of is like a conservation of where you are radially, right? Like I don't know whether you like had like in your experimental physics 1 lecture, like the professor kind of like sitting on like a on a rotating chair and like holding like some dumbbells and like pulling them in, or like the ice ballerina, you know what I mean, right? Like doing kind of the twisting. If you kind of conserve the momentum, you conserve the position radially. And this is exactly what's happening. Our particles do not drift radially if we have toroidal symmetry. And this is exactly what tokamaks have, right? So by design, and this is actually called Noether's theorem, if we have a symmetry, have a conserved property, thanks to Noether's theorem, tokamaks perform really good just by design. And this is something that stellarators don't have, right? Like we don't have that symmetry. And this is particularly important for trapped particles. So for example, for tokamaks, right, like you remember we had, let's look at the tokamak side, the right side here first. Oh yeah, cool. I can do it like this so that you're not distracted. So remember we had regions of high magnetic field here in the center and regions of low magnetic field here on the outside. Now I hope most of you know that you can have then particles being kind of trapped in a magnetic bottle, basically. So if we have a particle, because of the conservation of magnetic momentum, these particles will be reflected at a certain region where the magnetic field exceeds a certain value. Because of that, the particles will be forced onto so-called banana orbits or bounce orbits. So like these particles will kind of move along the magnetic field until they hit a region where the magnetic field gets too high, and then they'll be reflected and move down the magnetic field line again. In addition to that, they also experience a drift within the surface, which is why this banana orbit is kind of moving over the surface. And thanks to kind of the conservation of angular momentum, these particles don't at the same time also drift radially outwards. This is very different in stellarators, where we have these particles which on the one hand either are so-called passing particles, so like they have high enough parallel velocity that they're not reflected in regions of high magnetic field, so they'll just happily follow a magnetic field line along. But then we can also have different types of trapped particles, right? Because we have so many different regions of high magnetic field. So like we have a lot of high magnetic field here, but then the high magnetic field here is a bit different than the high magnetic field here. So really depending on where your particle is born and exactly what kind of parallel velocity it has, it can be mega locally trapped here in this well, or it can be trapped. Oh, sorry, this is a low magnetic field region. Got that wrong. Or it can be kind of half trapped, but then the next time kind of make it across the hump. And really the big question is, how do we confine all these particles if we don't have the symmetry? And just to illustrate this once more in a little video, here we have the trajectory of one of these passing particles, and you don't quite see it, but like right in addition, you'd have to think of like the helical motion around the magnetic field. But in general, like this particle is really following the magnetic field line along and really sticking to the surface. On the other hand, if we have a trapped particle, and here a region of low magnetic field is shown in blue, so the particle is trapped here and it's bouncing back and forth, but at the same time drifting radially outwards, and this particle would then soon be lost, right? It would be hitting, like let's imagine there's like the vessel here, it would hit the vessel here and then be lost. Yes. This is a particularly bad issue. If you kind of imagine we have, let me quickly, never mind. If we have these particles that are drifting radially outwards, then unless there's a collision with another particle, right, there's nothing stopping them from kind of leaving the plasma. So if we are looking at, this is a bit of a very theoretical plot, but if we're looking at the severity of the transport, basically, so like this is a diffusivity coefficient versus the collisionality nu here, then we have in stellarators very often this regime 1 over nu. So kind of the fewer collisions we have, so kind of the more to the left we go, the worse our diffusivity gets. And this is exactly this effect that that our particles are not stopped on their way out. This is very much in contrast to tokamaks, where, right, like remember in tokamaks, all the particles are confined. So for tokamaks, if there's no collisions, everyone's happy. So, no collisions, no neoclassical, no collisional transport. Only when the collisions start, you can have like some sort of like, the a particle being kind of brought from like one banana orbit to the next and then to the next, and then kind of slowly drifting out. And this is kind of what this curve is doing here. But considering that we want to go to very low collisionalities, and this might seem a bit counterintuitive, right? We're thinking, oh, we have like really high density for like lots of fusion reactions. We have high temperature, but actually this is Spitzer resistivity. So actually the resistivity goes down with the temperature. So actually in a reactor, we're exactly down here in this regime, right? And so if we're thinking of building a stellarator reactor with this kind of 1/nu regime, then this is not what we want. Like, we don't want so much collisional transport here. So how can we do it? Well, remember our Lagrangian, right? Where the Lagrangian kind of brings in a lot of the field geometry, or a lot of the kind of coordinates through the coordinates that the magnetic field strength depends on. Now, and really importantly, it's the magnetic field strength. This is not the B vector, right? This is just the magnetic field strength. Now, if we can somehow, through some magic trick, create a magnetic field whose magnetic field strength, not the vector, the strength, has some random ignorable coordinate, right? And here we've written the strength with like psi, so kind of the radial coordinate, theta, the poloidal coordinate, and phi, the toroidal coordinate. But like, this could be like really any coordinates, right? Like, just let's think of them at x1, x2, x3, like 3 coordinates in 3D space. And we somehow managed to write down our magnetic field strength in that way that it doesn't depend on one certain coordinate. Then this particular momentum is conserved. And this is exactly what we would want. And because then the particles would stay confined to the psi surfaces. So how do we obtain this? Through quasi-symmetry. So this is exactly basically what we've discussed here. We've created a magnetic field strength that only depends on 2, not on 3 variables. And we see this here immediately, right? I have here like 3 different examples of quasi-symmetry. And let's maybe start with a quasi-helically symmetric, because it's so obvious, right? You immediately see that if we were to, so like this is kind of like the magnetic field strength. If you take one of these surfaces, right? Like think of a torus, and you cut it open in the toroidal direction and then in the poloidal direction, and then you fold it open. And then this is exactly what you obtain here. So this is the toroidal direction, this is the poloidal direction. So you can immediately see here that if you, of course, if you ask like, oh, does my magnetic field vary along the toroidal direction? You say like, yes. Does my magnetic field vary along the poloidal direction? Yes. Okay. In the radial direction, it'll always vary, right? Like, this is something you have no control over. But then clearly, like this direction and this direction are just like not good coordinates for what we want. Instead, what you could do is like, oh, what if we walk along the diagonal, right? And then you just kind of invent another coordinate that kind of goes perpendicular so that you span a beautiful coordinate system. If you kind of only walk along here, these diagonals, then yes, then this is clearly a coordinate along which the magnetic field strength does not vary. And this is basically the trick. You only have to find a coordinate along which your magnetic field strength doesn't vary so much. In terms of quasi-axis symmetry, it's very tokamak-like. So here again, the toroidal direction, the poloidal direction, and here you actually see if you walk along the toroidal direction, your magnetic field strength almost doesn't vary. And here, quasi-poloidally, if you walk along the poloidal direction, your magnetic field strength almost doesn't vary. So these are ideas of how to create your magnetic field in a way that you have the same effect as in a tokamak, but with a very clearly twisted field, right? So you're basically tricking your particles into thinking they're in a tokamak because they don't know in which coordinate system they're supposed to think. And if you do this, and here we have Wendelstein 7x, which uses yet a different approach, then again we have our Does this work now? Sorry. I'm too impatient, clearly.
Is it a video that is supposed to play or?
Yeah, it's a video that's supposed to play.
Yeah, no, I'm not seeing it.
Now. Okay,
Now
cool.
I got
Sorry.
you.
Okay, so again, we're seeing the trajectory of the passing particle, right? Nothing new here, same as with the classical stellarator before. And now we're zooming into a region again of where the magnetic field is low. So we can again trace out a trap particle. And you see it's bouncing back and forth and it's drifting again within the surface, but it's not drifting radially outwards. And this is exactly thanks to what we did to the magnetic field, right? That we kind of tailor the magnetic field so that the particle will not drift radially outwards. If you compare two different devices, so here at the bottom we have a very classical stellarator, and here we have a quasi-poloidally symmetric stellarator, so an optimized one, and you trace particles and you just kind of count how many are getting lost in their path. Then you would see that a lot more are being lost here than here. I'm so sorry, the video is not working. Let's continue. So I've already shown you many different shapes, right? Like we've seen the figure 8 stellarator, we've seen Wendelstein 7X, we've seen the quasi-axisymmetric stellarator, NCSX that was being planned in Princeton. This is HSX. This is LHD. There's infinitely more shapes. So which one performs the best? And this is really not so easy of a question because so in tokamaks you have generally like 3 shape parameters, right? You can ask how triangular do you make your flux surface, right? Like when you cut it, do you make it like very circular or do you make it very triangular? How elongated do you make it? Like do you make it kind of flat like a pancake or like really elongated? And then how square do you make it? In stellarators, there is something like 40 different shape parameters. At least that's kind of what people have kind of investigated with a singular value decomposition analysis. And if you now think you only kind of take like 10 different kind of levels in each of these parameters, right? Like 0 being we don't have this parameter, like this shaping ingredient at all, and 10 being we like fully have it. And you only split it into 10 levels, which is not a lot, right? Like you could split it into 100, but let's go with 10. Then you'd have 10 to the 40 different 3D configurations that are possible for stellarators. Whereas we have like 10 to the 3 for tokamaks. So we have clearly a combinatorial explosion. So like this is more than we have visible stars. This is more than we have bacteria on the Earth's surface. So how do we find the shape that could be a potential reactor candidate amongst these 10 to the 40 configurations? So there's different approaches, right? In the old days, what was done was kind of like, let's see what we can build and let's see what it gives us, right? So like this was kind of the idea behind the figure 8 stellarator. So you kind of, they made the coils, they twisted the axis, and then they obtained a certain shape. This is, you can also kind of see this a bit in the heliac and the torsatron, right? You combine coils, obviously in a clever way, right? Like with quite some thought behind it. But like, you know, like these coils, there is not a lot of flexibility in terms of, oh, let's make the plasma so that our particles don't drift radially. And you can tell because like all these devices have issues in terms of particle confinement. Another approach is to first think about the physics you want to have, like the physics properties. Therefore, you optimize the plasma boundary first so that the plasma boundary, the magnetic field shape is exactly the way you want it in terms of physics. And then you try to make coils for this. This doesn't always work. So people have found beautiful magnetic fields with exciting physics properties only to then go and find that no coils can be built for this. But we're getting better at this as well. Yeah, so there's advantages to this, right? So like one learns about the plasma boundary effects. So one learns how the coils affect the plasma that's possible. And of course, we can first find an equilibrium and only then do the coils. And we'll probably only calculate the coils for, I don't know, our 5 favorite configurations, right? We won't do the computational cost of finding a coil set for each of them. But it also has the issue that not in every case coils might be found. So you might get, hung up, or you might fall in love with one particular configuration only to find that there's no coils for it. So what would we want to optimize for? So like there's in the end 3 things that we'd want a feasible stellarator reactor in the end, right? We want sufficient confinement. So we don't want our particles to drift outwards, and we want MHD stability. So this would count for linear ideal MHD stability, nonlinear ideal MHD stability, resistive MHD stability, and other issues. In terms of confinement, we want low particle drifts of both deuterium and tritium, but also of the fast particles. And these are actually quite the challenge. We want low neoclassical transport, right? Like think about again about the 1/nu regime. We want low turbulent transport and others. And then we want low costs ideally, right? Like we want to be able to build this. So this goes into size of the machine, the complexity of the coils, the materials that are used, how much of the material do we need, and so on. And ideally everything at the same time. Luckily we have big codes to do this, but now imagine you'd have a code and you'd come up with like a shape, and then you would calculate, you'd kind of start your big fancy codes and calculate all of these, right? Like you'd run a big fancy MHD code to calculate, is this particular shape MHD stable? And then you say, sadly not. And then you kind of go back to, make a new shape, and then you calculate it again, and then you calculate with a big fancy code the turbulent transport and so on. So you can't really do that, right? Like you would never get through like the big configuration space. So what we do instead is we use so-called proxies, where we say, okay, certain criteria have been found that give us an idea of like, if we stay below this number, for example, then we are MHD stable. And we don't care how well MHD stable we are, but like as long as we're like below this threshold, for example, we're good. So for example, for ideal MHD stability calculations, we can use the so-called Mercier criterion, which is still fairly involved. But what we can do instead is the so-called magnetic well, which is a property that can be super easily calculated. It's just like an integral along the magnetic field line. This is just like one example. Or another thing to check for ideal MHD stability is the rotational transform. So for example, we would want to avoid rational numbers. So where like rational numbers in terms of like where really like with like X numbers of toroidal turns and M number of poloidal turns, we're exactly at the same end, because then we get resonance effects and islands, and generally MHD stabilities can become quite evil. And calculating the rotational transform is mega easy as well, right? So like that's a very nice proxy already. Then another proxy that's frequently used is that for neoclassical transport. So I already showed you this picture here, the collisionality and the diffusivity, so kind of the severity of the transport. And you can calculate this diffusivity coefficient with, again, fairly fancy codes. But what you also find is that, and then technically you'd have to kind of calculate this for like every single particle. But then you can also boil this down into a so-called effective ripple, which is kind of like a shorthand for like everything that happens for like all the different types of particles. But like it's boiled down into one number, and then you only calculate this for like a given machine once, and then you optimize for this basically. And then, for example, this is also a very nice feature to compare different machines. So here we're plotting this effective ripple. So kind of this is basically a how bad does this get up here, right? Like this 1/nu regime, how horrible does it get? For different radii. So like, I mean, like the radii don't matter so much. So let's, I don't know, sit here at like 0.6. And then we see here, like ITER is down here, right? I mean, ITER is a tokamak, so has very low neoclassical transport. A rippled tokamak with 1 filament per coil, so like far fewer than ITER has, already has higher neoclassical transport. D3D, the tokamak, also has quite some neoclassical transport compared with ITER. But then, like, look here, we're in a logarithmic scale. The stellarators are all up here. Yeah, there was quite some work to do, but like there have been quite some cool advances in recent years. Generally, what you then do for stellarator optimization, you have a big code. There's like various codes, Stellopt, ROSE, SimSopt, depending on which you want to use. And usually you start with your plasma boundary, right? Like you start with like one certain shape that you think that would be a cool starting point. You solve the magnetic equilibrium with some code, VMAC or something, and then you calculate all your physics targets. You calculate all your numbers, all your proxy numbers. You calculate how horrible is the turbulent transport, how high is our epsilon effective, our neoclassical transport, how are we doing with MHD stability, and then you're seeing, then you have some number, then you kind of make a little adjustment in your optimizer, right? You kind of go a tiny bit in one certain direction. Like, let's say you kind of make a little dent in one corner. So this is the adjusted boundary. Then you solve the equilibrium again. Then you kind of calculate your targets again. And then you say like, oh, did we get better? Cool, then let's walk in the same direction further until we hit an optimum. Or you say like, oh no, this got worse. Let's return. Let's kind of go in another direction. This is what these optimizers do. Let me skip that. So this is like generally how things are done, but of course, depending on how clever your physics ideas are that you kind of put into these simplified questions, that will tell you how good your outcome can be. And one of the most clever things that have been done in recent years in terms of stellarator optimization is the so-called precise quasi-symmetry. So people found a way to make this kind of, like, remember like these three different shapes that I showed you, where I showed you like, oh, if we choose the right coordinate system, then we have like this quasi-symmetry, like this one weird coordinate along which things aren't changing. So Matt Landerman and Elizabeth Paul found this way of coming up with really like high precision quasi-symmetry with like a very cool method where they kind of construct these like from the axis outwards. And here again we have it's a slightly different measure, but basically here we're showing the symmetry breaking magnetic field Fourier coefficients BMN. And the more of those we have, the more wiggly and the like the less symmetric it is. And here we have again the radial location. Again, let's sit at one certain radius. Like let's again choose 0.6. And here in green, for example, we have NCSX, the little quasi axisymmetric stellarator that was planned in Princeton. And here in solid lines, we have all these different new machines that came out of their work, and again, orders of magnitude lower. We're really reaching levels where stellarators are basically as symmetric as tokamaks in a sense, like when it comes to like what will be important for the stellarators. So the good news is that, so like this sounds all really theoretical, and you might think like, can we actually kind of do this? Can we build this? This has been experimentally verified on the HSX accelerator. So here they measured the electron heat diffusivity, so a measure for how much are kind of particles drifting outwards in kind of in QHS. So this is the quasi-helically symmetric configuration of Anderson 7X, and then the mirror configuration. So like they changed some coil currents and basically destroyed the full quasi-symmetry. Like they didn't go all the way in terms of destroying, but like they made it worse basically. And they found that the heat diffusivity is in fact much higher for the mirror version than for the perfectly quasi-helically symmetric version. And then they calculated the neoclassical transport, and they showed indeed that the mirror configuration had much higher neoclassical transport. So this difference here in how good the heat was confined was indeed the quasi-helically symmetric QHS was much better because the neoclassical transport was better, because the quasi-helical symmetry was better. let me see. Okay, let's briefly come to Wendelstein 7X. So Wendelstein 7X, as I already said, was designed to have a long operation time at reduced plasma current, and with kind of two additional questions, basically, that we really have improved particle confinement, a bit like HSX, but also to be able to do this for very high plasma pressures, because in the end, there's no use in having this work very well if there's only a teeny tiny amount of plasma in it. But we need this to work when there's reactor conditions, right? So we need a significant chunk of plasma in the machine. And as you can imagine, the plasma is still like a hot gas. So it'll push back against the magnetic cage and kind of create magnetic perturbation. So this is where kind of these MHD instabilities come from. And if you get this to like a higher number, and 5% is a good number already, then you can say you could have a significant plasma density and temperature in there, and the magnetic cage would still kind of sustain that. Yeah, and Wendelstein 7X works fairly well. So we have indeed reduced neoclassical energy transport in Wendelstein 7X, which is kind of shown here with this figure. And we have Wendelstein 7X and then compared against LHD. But we have quite some other issues still open. So it's yeah, that we could and might still optimize for. So for example, the magnetic well isn't always a good proxy. And then the neoclassical transport optimization is a great first step, as we've seen with HSX and Wendelstein 7X. But it seems like we might also want and need turbulent transport optimization. And this is what we found in Wendelstein 7X. And for time reasons, I will skip this, even though it kind of breaks my heart, because this is work by my PhD student, Ralph Mackenbach, and he did some cool work there. But alas, kind of one final thing to kind of go a bit more in the engineering direction and away from the physics is that, of course, we also still need to think about coil optimization, right? So if we have a plasma and we kind of want to create a certain magnetic field to confine it, then, let's think of like one coil that would do it. Cool. But then, of course, like this coil here with like this weird little arm out here, but like, let's imagine the difference between the two wires will be teeny tiny. Then the magnetic field perturbation that this coil would create would be basically negligible compared with this. So if you have an optimization code that's ignoring, for example, length of the coil or complexity of the coil, then this would be a perfectly fine solution. But imagine building this, right? So like as a coil designer, you must impose constraints. And some of them are, for example, that you define a winding surface, then you define like where you want your currents to be on the surface, right, to create the magnetic field. And then you discretize your serves into the curves, and then you design the coils from these shapes. And then you kind of can create like fairly good coils nowadays. And this is really important. For example, here we see NCSX again, like the stellarator that was supposed to be built in Princeton. And you see here the coils, right? And you see like the bends and twists that they make. And these bends and twists were one of the reasons that the coils became extremely expensive, so much so that they stopped the project, sadly. So really reducing the complexity of the coils and increasing the tolerances really can reduce costs and make stellarators more attractive. So this is really a really important goal in stellarator design. And I will skip this. Just very briefly, stellarators with their certain benefits have thanks to their certain benefits, there's quite a few stellarator startups, or let's call them the fusion industry, because some of them are really not that small anymore. We have quite a few in the US. We have Type 1 Energy, Thea Energy, and StellarX. And in Europe, you've just kind of talked to all three, Proxima Fusion, Gauss Fusion, and Renaissance Fusion. I'm very excited that they were all stellarator startups. Yeah, so there's really a lot going on in terms of stellarators with the fusion industry, and I really can't wait to see what they're coming up with, how they're working with with academia together so that we can hopefully have the first bigger stellarator machine in the future. And yeah, just a tiny bit of advertisement. So if you are interested in internships or like ever want to do a PhD in the future, you know, like either drop me an email or apply through the HEP graduate school directly. So if you like directly want to go for a PhD here in Greifswald, in the north of Germany, it's an admittedly small town, but it's quite cute. And we have the coolest fusion machine in the world. So you'd be very welcome to join. And with that, I would like to thank you for your attention. And I know this was long and a lot, but really thank you so much.
Josefine, thank you very much for this really interesting presentation. Just long, but I think you managed to bring all the concepts and also the energy behind the stellarators concept also by yourself. And thank you so much for providing this presentation. I know you've been quite busy lately, so I appreciate that your enthusiasm for stellarators took the best out of you, and you managed to be here with us on this event.
Happily so.
So yes, so now the chat is open for questions. Perhaps one of the first question and the most recurring one, it's if it is possible to have your presentation available, because people find it really interesting. So we can decide later, maybe we provide this recording to the students, or maybe we share the presentation. But overall, what do you think? Do you think it's possible to share this?
I think generally, yes, of course.
Okay.
Of course. Like maybe like if you have it like with a like password or something, that'd be kind of nice.
Okay, then we can discuss, and then we will let you all know how you can access this Josephine's presentation. I think it's really, really important. There is a question for you. Maybe can you see the chat, Josephine? Maybe because
I do, but like it's
the very last from Diogo.
Okay, Can you explain better in slides 34? Okay. Ooh. Okay, let me share my slides again. Okay. Oh God. Okay, yeah, I'm fast enough, I think. Okay, maybe not. Oh yeah, I am. There we go. Okay, so the question was how do if we manage to create a magnetic field, right? That only depends. And again, like these are kind of the usual coordinates, right? Like toroidal coordinate, poloidal coordinate, and psi being kind of the radius. But these, like, don't think of those anymore as like the typical Tokamak coordinates, right? Like be like really free in your coordinates, right? Like don't have a fixed idea of what they should be. But imagine you can write down a magnetic field that only depends, like it'll always depend on psi. But then imagine you can somehow come up with a new coordinate that along which the magnetic field is constant, and then like a third coordinate which is kind of perpendicular to the three, so that you have like again three nice coordinates, a bit like we did here, right? Like instead of being like phi and theta, we use, I don't know, let's call it h, right? And that will be the coordinate along like a linear combination of the old phi and the old theta, and along this h coordinate, our magnetic field now doesn't change, and then we have a new coordinate h2 or something. And let's imagine we'd have now b of psi, right? Like again, our radius will always be the same, and then h and kind of h2. But then we've just seen that if we were to do kind of this derivative here, we kind of do the Euler-Lagrange equations, and we write down the dB by dH, then we would have a 0 here, because that's exactly the coordinate along which our magnetic field doesn't change, right? Then we would have along this particular kind of, we'd call this then pH, this would then be, because nowhere else in the Lagrangian do the direct coordinates really appear. We only have time derivatives of the other coordinates appearing. That's kind of the beauty of the Lagrangian. It's kind of magical. Because we basically created our magnetic field like this, we'd immediately have conserved momentum in this new coordinate. So like this would not be phi, but like it would be this h. But then this would mean immediately that our particles would stay confined on these psi surfaces, on these radially surfaces. So just because here's a phi and here's a phi, that's replaced by an H, that kind of doesn't matter, right? Like in the end, we've just kind of, you know, like if you kind of imagine, let me draw this real quick. In the end, what we've done is we've gone from a coordinate system like this. Sorry, this is like very weird now. Do you see anything? I think you don't, right? 'Cause it's
No, we
blurred.
don't. Yeah.
Oh, this is great. Where am I even? Where is my Zoom? Okay, like then let me do it like this. We've gone from like an XY coordinate system that was originally like this, or like theta phi, really doesn't depend. We've just kind of tilted it a tiny bit and maybe made it a bit wiggly, right? It's like that's the beauty of curved coordinate systems. Just so that kind of our maths shows us that there is a conserved property here. Yeah, I hope that helped.
Okay, Josefine, thank you very much. I guess also for the students here present to know, Josefine is a wonderful PhD and master student thesis supervisor, not say by her, but by her students, which is the most important. So if you are interested in working with Josefine on the field that she's working on, you can, I think they can contact you, right, Josefine? You're
Yeah, please do. I'll write it's like josefine.proll@ip.mpg.de. There you go. Just drop me an email.
all
Or
right, good.
contact me over LinkedIn or whatever, you know.
All right, Josefine, thank you. Thank you very much for being with us today. And yeah, and we stay in
All right.
touch and wish you a good rest of the day. Thank you so much.
Thank you. You too. Bye-bye.
Bye.